Now, electromagnetic induction lesson 5. Let us discuss four numericals. The last numerical is very important for your competitive exams, and the first three are for your school exams, right? So let us begin with the instantaneous magnetic flux phi in a circuit is given like this. Phi is equal to 4t square minus 4t plus 1, means phi depends on time. Therefore, d phi by dt has some value, and we know EMF was minus n d phi by dt. N was indicating the number of turns in the coil or the circuit. In this case, since it is not given, so we take n is equal to 1. The negative sign was indicating only Lenz's law, that indicates the direction of current only. Now, the total resistance of the circuit is 10 ohm. The circuit through which this flux is associated and it is changing, and the resistance of that circuit is 10 ohm. At t is equal to half second, the induced current in the circuit is how much? First choice, 0 ampere, 0.6 ampere, 0.4 ampere, 0.2 ampere. Very simple. We know EMF is equal to d phi by dt. I have not taken the negative sign, only the negative sign indicates the direction of current. So I am taking the numerical value of it. So the current will be voltage over resistance. EMF is also a voltage, so EMF over resistance. And EMF we did in Faraday's law of electromagnetic induction, d phi by dt over R. R is a constant taken out, so d phi by dt. So 1 by R d by dt of phi. Phi is given as 4t square minus 4t plus 1. That is why I have written here. When this is differentiated, this with respect to time, this 2 comes here, it becomes 8t. 4 is taken out, dt by dt is 1. And derivative of 1, constant is 0. So the derivative of this with respect to time becomes 8t minus 4. And it is asked to find out at t is equal to half second. So put t is equal to half second and put value of R, that is given as 10 ohm. So this 4 minus 4, 0. So the current comes out to be 0. Now let us go to the second numerical. A varying magnetic flux means magnetic flux is changing. Linking a coil means the flux associated with the coil, magnetic flux is changing. Means d phi by dt. Since this is changing with respect to time and this was your EMF, therefore there is an EMF induced. And that phi is given as xt square dependent on time. If at any time t is equal to 3 seconds, the EMF induced is 9 volt. EMF is given, time is given, flux is given. Then the value of x is how much? Given as minus 1.5 Weber second inverse, 3 Weber second to the power minus 2, second to the power minus 2, 6.66 Weber second to the power minus 2, minus 0.6 Weber second to the power minus 2. How x will be this? Because from here, if you keep x on one side, bring t square to the other side, so your x becomes phi over t square. Phi is measured in Weber, the flux. Time is in second. So Weber per second square. So that will be the unit. Weber per second square, Weber per second square, Weber per second square. Let us discuss. Now, given, very simple, given phi is equal to xt square, so EMF is equal to minus d phi by dt, minus, why I have taken the minus sign? Because the flux could be entering or the flux could be coming out. The flux could be increasing or the flux could be decreasing. So differentiation of this comes out to be minus x2t. At t is equal to 3 seconds, EMF is given as 9 volts. So for E put as 9 volts. This is minus x 2 into t. T is given as 3 seconds. So minus 6x is equal to 9. So x is equal to 9 over minus 6, that is minus 1.5 Weber per second square. So how it is Weber per second square? I explained, because phi is xt square. So keep x on one side. it becomes phi over t square. Therefore, phi is Weber, t is second, so Weber per second square. Means, and we know flux is equal to BA cos theta. So B is equal to phi over A cos theta. This is the unit of area, right? So this negative sign means it is decreasing, right? Flux per time square is decreasing. The negative sign indicates it is decreasing. Now let us come to the third one. Third one is simple. A coil of cross-sectional area 100 centimeter square is placed in the magnetic field which changes to 4 into 10 power minus 2 Weber per centimeter square. This is also given in centimeter square. This is also given in centimeter square. So there is no need to convert to meter square. Within 5 seconds, means from 0, initial flux was 0, and from 0 it changed to this. What will be the current across a 5 ohm resistance? And the choices are given like this. Simple. Area is given, 100 centimeter square is constant. B is changing, magnetic flux field is changing to 4 into 10 power minus 2 Weber per centimeter square. R is given. I am not changing the units to meter square because both are given in centimeter square. Now look at, any current is voltage over resistance, and the maximum value of voltage is called EMF, that we studied in current electricity, so EMF over R, and EMF is d phi by dt over R. I am only interested in the current, not the direction of current, so I have not taken the negative sign. So any flux is equal to field into area into cos theta over dt. Now since area is constant is taken out, R is constant taken out, so dB over dt. Means how the field is changing with respect to time. I have taken theta as 0 because it is not given. I am taking it as 0. Theta is 0 means magnetic, if the magnetic fields are into and into, then the area is also into, means angle between them is 0. So I put the value of A, put the value of R. Flux, initial flux was 0. Final flux is 4 into 10 power minus 2. So the change of flux is phi 2 minus phi 1. That is, this minus 0 is same thing as 4 into 10 power minus 2 divided by time is given 5 seconds. This comes out to be 0.16 ampere. I have not taken a negative sign because I am not interested to find the direction of current. So that is the third one. Now the fourth one is very, very important. Before you do this, you must go through my EMI, electromagnetic induction lesson 4 in my previous video. After doing this, then look at this numerical, very, very important, very, very important. I tell you time and again. As shown in the figure, a rod AB, this is the rod AB, from here to here, this is the rod AB, shown in black, in the plane of the paper. Its length is L, is moving in the plane of the paper, in this case towards this side. And in my video, I had explained this rod AB moving to left hand side. Now it is moving to this side. In the video, the length was L. Here also the length is L. In the video, the magnetic field was into. Here also the magnetic field lines are also into the plane of the paper. Plane of the paper with a velocity V. With a velocity V, it is moving to this side. If R is the resistance of the rod, this rod, from here to here, this rod has a resistance small r. If R is the resistance of the rod AB and capital R is the resistance of the rail, look at this rail. This rail, which is connected by a wire here, DC, whose resistance is capital R. This rod AB is moving to this side. Find the current and direction of current if a B is into the plane of the paper. Very interesting. Now look, when the rod is here, then this is the area it is creating, A, B, C, D, A. And look how many number of lines of force are passing through this. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. 4 into 3, 12 lines of force are passing through this, normally through this area. Now, if the rod AB is moving to this side, suppose AB is now here, then the number of lines of force passing through the area increases. Means there is a change of flux. So since there is a change of flux, there will be EMF. And we had derived in EMI lesson 4, when a conductor lying in the plane of the paper and the magnetic field is into, when the conductor moves to this side or this side, the EMF developed was equal to BLV, where B is the magnetic field, L was the length of the conductor, V was the velocity of the conductor. When AB was moving towards left, that is what I explained in my lesson 4 video, when AB was moving towards left, EMF was BLV and the current was from A to B when this was moving towards left. Here it is moving towards right. So the current will be from B to A. Current will be from B to A. I will explain you. Wait, and so I replace AB, which is developing an EMF BLV by a cell of EMF BLV voltage, and its resistance is R. I have shown it here, and this thing is same thing as this thing. Means this point is C, this point is D. So now you have a complete circuit having EMF BLV and two resistances in series. So now I will explain. Now why the direction of current will be from B to A. Now if AB is moving towards right, as in this numerical, flux through the area ABCD is increasing. As AB is moving towards right, before moving the number of lines of force passing through this was 1, 2, 3, 4, 4 into 3, 12. If AB is here now, then the number of lines of force passing through this has increased by 3. Means flux is increasing. Then, according to Lenz's law, the direction of current should be such. It will try to decrease the flux. That will be possible if AB experiences a force to this side. If AB experiences a force to this side, then the area A, B, C, D, A will decrease. So less number of lines of force will pass through this. That is, the flux will decrease. So AB to experience a force to this side, the direction of current in AB should be from B to A. From B to A. From B to A. Means if this is the direction of current, IL is to this side and magnetic field is into. So using the expression IL cross B, this expression, AB will now experience a force towards the left. That is, it will decrease the flux. According to Lenz's law, to decrease the flux, because AB is moving towards right, the flux is increasing. According to Lenz's law, it should decrease. So what should be the direction of current so that AB experiences a force to this side? Then only the area will decrease. Since the area will decrease, the flux will decrease. So AB should experience a force towards left. Then the flux will decrease because the area will decrease. So I is from B to A using this expression. If I is to this side, so IL is to this side, and magnetic field is into the plane of the paper. So IL cross B will be towards left. So the current is from B to A. So the moving rod AB across which EMF developed is BLV can be represented by a cell having EMF BLV and having internal resistance small r. And if you look at this circuit, that is same thing as this circuit, then the resistance of the rod AB, the resistance of the rod AB, which I have shown it here, small r, and this capital R, they are in series. So the effective resistance is equal to R plus R, and the voltage is BLV. So the current will be voltage over the effective resistance, that is R plus R. Very, very important, right? Very, very important, right? So this is the direction of current, right? Very, 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 very important.